Hello, everyone. Welcome back.
Good
Today,
afternoon.
good afternoon. Good afternoon. And there's very few of you here as the beginning of the class, but we're going to get started anyway because we're going to do new stuff today. We're going to talk about graphs. Before we get started, I'd like to find out if anybody has any questions about anything that we have done so far, and where we're going from here. So anybody have any questions for me?
Just nice haircut today.
Say that again, Caitlin. Sorry, I didn't hear you.
Nice haircut today.
Oh, thank you very much.
You said you were gonna get a haircut. You got a bad hair day on Monday.
I needed it really badly. I needed it really badly. I got it yesterday. I feel so much better. Thank you very much, Caitlin. Thank you. Everybody.
You're welcome, Reza.
All right, homework. Let's talk about homework for a second. You have homework 6.
Yeah, you already posted it, yeah.
Yeah, homework 6 is due this Sunday. Okay, currently it's due this Sunday, and I've been looking at the schedule, and we don't. You guys, the good news is for you is there is no homework 7. Okay, homework 6 is the last homework, and I will extend the homework 6 to end like on the 16th as opposed to on the 9th. Okay, it was originally due on the 9th, but now it's going to be due on the 16th for homework 6. Any questions about that? Just remember about homework 6, when you download the binary search tree that we did in class, it comes with a tree iterator that is not the tree iterator that you need to use with the homework. Okay, the tree iterator that we did in class, I named the functions slightly differently. So don't use that one. Use the one that comes with the homework. Okay, I announced it in class yesterday, and I noticed that there are some people who are still using the old tree iterator, the one that we did in class. Use the one that comes with the homework. There's a link to it in the homework. Please download that one. Okay, use the binary search tree that is in the homework. Use the everything that is in the homework. Don't do anything from the examples. Okay, so any questions? Okay. All right, so let's get started with what we want to talk about. Let's talk about graphs. So what are graphs? I'm going to share my screen when this comes up over here, and we'll talk about what that really means. Okay, so a graph. What is a graph? Okay, graphs are a representation, okay, of vertices, okay, and edges that connect them. Okay, so a graph, think of it as a map. Okay, it's called a graph in computer science, but think of it as a map. So if I have vertex A, vertex B, vertex C, vertex D, and vertex E, I can have edges that connect these graphs. Okay, so like that. This is a graph. Okay, this is a graph that shows that has 5 vertices and 1, 2, 3, 4, 5, 6 edges. Okay, this is a graph that shows 5 vertices and 6 edges. Okay, what we term 2 vertices as being adjacent. Okay, if there is an edge that connects them. Okay, so the adjacent vertices in this graph are A and B are adjacent, B and D are adjacent, right? A and D are adjacent, D and C are adjacent, C and E are adjacent, and D and E are adjacent. Okay, a path, when we talk about a path through the graph, we're talking about a sequence of edges leading from a source vertex okay, from where a starting vertex that we'd start from, okay, and ending at the vertex that we want to have a destination go to. Okay, so if I'm looking for a path between vertices A, sorry, A and C, okay, I have a couple of multiple paths that go from A and C to A and A to C. Okay, so here's a path that goes from A to C. Okay, there's another path that goes from A to C. It goes like this. Okay, that's another graph. Okay, another path. Here's another path here. Okay, the length of a path is the number of edges that you traverse in this kind of graph, the number of edges that you traverse to get from the source vertex to the destination vertex. So the pink one, the pink path that I'm showing you there has a length of 3. The orange path has a length of 3. The green path has a length of 2. So the distance from A to C, the minimum distance from A to C is 2. Okay? And the maximum distance in this case, what we have highlighted here is 3, but there's no such thing that restricts us, okay, unless we force that to happen. If I'm doing a path from A to C, there's nothing from stopping me from going like this. I'm like a wanderer, right? A to B to D to A to B to D to E to C. Okay, that's a path that has loops in it. Okay, but it's still a path. It's still a path, and just want you to be aware of the fact that that is considered a path. Okay, so why do we use graphs? I mean, what's the important thing about graphs? Well, the most important part that we use on a regular basis now is GPS. Okay, is GPS, and we use GPS all the time in everything that we do. Like even when I know the way to where I'm going, I usually put the GPS on in my car. Okay, because I want to know about traffic. If there's traffic, I want to be rerouted. I want to find a better way to go. Okay, how does GPS work? Well, GPS works as a graph. Okay, we're going to deal more. So if I was to look at, I don't know, let's pick Midtown Manhattan, for example. Okay, Midtown Manhattan has streets that go east to west. Okay. And then they have avenues that run north to south, north to south. Okay. That's a straightforward lattice grid like this in Midtown Manhattan. Okay. And you can think of yourself as being at a particular intersection. Okay. This is the source and this is the destination. Okay, so how do you go from that source to that destination? Well, GPS will essentially figure out that there is a path, for example, that takes you like this from the source to the destination. But there's another path that goes from the source to the destination as well. Here's a path that goes from the source to the destination, right? And which one of them is shorter? Well, the yellow path is 1, 2, 3, 4, 5, 6, 7 edges. And the purple path or the pink path is 1, 2, 3, 4, 5, 6, 7 edges also. Okay, so they both have the same length, same distance as far as number of edges. Okay, GPS is actually interesting because the edges are not just all equal, right? The edges are weighted. We're going to talk about weighted edges later on. So the distance from here to here, okay, this could be a distance x, and the distance from here to there could be a distance y. There are different distances, right? GPS on our phones and in our cars or whatever you get your GPS from, your GPS basically has weighted edges, and what it uses for weights is the amount of time it takes to get from point A to point B on the average. Okay, So if it takes a minute to get, then X is a minute. If it takes 5 minutes to get from this vertex right here to this vertex right here, then Y is 5, okay? And then we calculate the distance by adding all the weights together to find the shortest path to go from point S from the source to the destination. So GPS is one thing that we could do. The other thing that that we could use graphs for are for, you know, social networks, professional networks like, I don't know, Facebook, LinkedIn, so on and so forth. So you lay out, you know, the people and the people. So if you have a person and this person, person X knows A, B, C, and D, knows 4 people, and person B knows another 2 or 3 people, okay? W, X, and Y, okay? And person A knows 2 people, F and G, and person C knows 2 people. They are H and I also knows W, and H also knows D, right? And that Y knows F, right? That forms a graph. And if the system is trying to figure out who you may know, so if you are person X, it finds all the people that you know directly, and those are the ones that you can reach in one hop because you are directly connected to them. These are the people that X knows directly. And then Facebook, Instagram, LinkedIn, all of these networks, they usually then can say, oh, maybe you should know G. G is somebody that you may know, or F is somebody that you may know because they're known by somebody that is known to you, okay? So traversal of the graph is very important in social networks because you build this network and then you find out all the connections between all the people, okay? You can imagine that something like that is done for products as well, right? You know, person X, you know, looked at an Xbox set, okay? Person G looked at an Xbox set to buy. Oh, well, not only does X like Xbox and G likes Xbox, but it looks like X and G are both friends of A. Maybe they should become friends themselves, right? Because they both like Xbox. Social networks is all about graph traversals, okay? That is really an important way of them basically doing the business that they do, monetizing, making money off of our behavior and our connections, okay? That's how they do their business. Another application for graphs is networks, actual computer networks, okay? Computer networks, those of you who have not taken the networking class yet, computer networks are set up. So I'm going to draw, this is the wrong color. I'm going to draw a network as a little cloud. Okay, here's another network. And here's another network. And then here's another network. And these networks are connected to each other, and there are routers that connect these networks to each other. Okay, these networks are all, there are routers that basically connect networks to each other. Okay, so this is network 1, network 2, network 3, and network 4. Okay, so router 1, router 2, router 3, and router 4. So router 1 can reach networks 1 and 2 directly. Router 2 can reach networks 1 and 3. Router 3 can reach networks 2 and 3. and router 4 can reach 3 and 4. Now, if I am sitting at a computer that is connected to network 1, and I want to send something to a computer that is connected, we call these computers hosts because they're different from routers. There's hosts because they're hosting some application or some person sitting at them. They're hosts. So if I want to send a message from host 1 to host 2, then the message clearly can go several different ways, right? There's multiple paths that takes us from one to the other. Here's one path. Here's another path. Right? These are all different paths that go from network 1 to network 4. In order for these routers to know what paths are available, the routers exchange information with each other. So when router 1 wants to tell his neighbors, the neighbors for router 1 are routers 2 and 3, because router 1 connects to router 2 through network 1, and router 1 connects to router 3 through network 2. So when router 1 wants to tell him the neighbors that what he has access to is, he sends a graph. He says, one of the ways that they do this, the routers, is router 1 sends a graph, says network 1 and network 2, and I'm router 1 in between them. Okay, router 2 has a similar graph, which says 1 and 3. So when router 1 sends his graph to router 2 looks at the graph and says, how can I connect that graph to my graph? Well, clearly we have edge number 1 in common. So really, what is the story here is that really this is a connection. And router 2 will form that connection. And it'll say, oh, okay. And eventually router 2 will hear from router 4, and router 2 will form a connection that says, oh, look, I can connect through network 3, I can connect to router 4, and on the other side of that is network 4. So once routers build these graphs, then they can now find a way of moving your message from one network to another. And that is all done using graph algorithms, using graph information. Okay, so these are applications among few of the applications that we're going to talk about. Okay, there's many more applications to graphs, and there's actually a really interesting course that is offered here at Lehman, which has got to do with graph algorithms. Okay, and we're going to touch on some algorithms for graphs here, but if this subject interests you, then you should look into this graph algorithms class, which is offered here as an elective. And because you'll spend the whole semester exploring the beauty of how to do work inside graphs and what are the algorithms and what's possible and so on and so forth. There's a lot of stuff that can be done with graphs, and we're only gonna just like touch the surface of it here, okay? Any questions so far? How are we doing? Everybody okay? All right, so let's continue, as long as everybody is okay. You guys are surviving so far. Okay, so what else do we want to talk about graphs, okay? Well, how do you represent the graph? I mean, what does a graph look like when Ajani, go ahead, you have a question.
Yeah, sorry, on the last graph, this is a question. For vertex B and C, you didn't connect those. Is there a reason why, or is that just the
Which one? Over here?
The one before that?
This one?
Oh, that one, yeah.
Yeah, because we don't have a path from B to C in this particular graph.
Oh, okay. But like if you were to create a graph that had all of them connected.
If I added another edge over here, then yes, sure, I have yet another edge that connects them. But the way I drew the graph earlier, was not there.
Okay, just for this example. But I'm just saying, like, if you were to do a different graph, you could have it set up that way.
Yeah. There's no limitations as to where the edges can be. Okay. I'm not saying that there can't be an edge between B and C, just that the graph that I chose did not.
Okay, all right.
Okay. But a graph could potentially have an edge between B and C, but the graph that I chose did not. Okay.
Okay, all right, thank you.
It's not, it doesn't mean anything in the real world. Okay. So how do I represent the graph? Well, one of the representations of graphs is something called an adjacency list. Okay. An adjacency list. So let's take a sample graph over here. I have A, I have B, I have well, let's take the graph that we just did over here, right? A, B, C, D, E, right? Let's do this one. A, and let's draw it again. B, C, D, and E, right? And we said the edges looked like this, right? So this is the graph that we had earlier. So what is an adjacency list here? When we say vertices are adjacent, we said vertices are adjacent when there's an edge that connects them. So if I was to say for vertex A, what are the adjacent vertices to A? Okay, so vertex adjacent. So the vertices that are adjacent to A are B and D, right? Vertex B has A and D, right? Vertex D has A, B, E, and D. Vertex E is adjacent to D and D and A, B, C. No, this is vertex C over here, sorry. Okay, this is vertex C. Vertex E is adjacent to D and C, and vertex C is adjacent to D and E. So this would be the adjacency list for this particular graph.
You have to probably change the vertex D, what it's adjacent to, since you just changed that to C, just to have it match.
Vertex B?
Vertex D.
Oh,
Yeah.
vertex E, D, right. So that should be C over here, right? Thank you. Okay. So this would be the adjacency list of this particular so what's the advantage of using an adjacency list graph representation? It's basically there is every edge is appearing in here twice. So the edge between A and B is appearing over here and over here, right? This edge is appearing twice, okay? The number of vertices is, and each edge appears twice. V refers to the number of vertices, okay? So the order of this is order of V plus E, okay? It's really order of V plus 2E, right? But since we're taking big O notation, we don't really bother with the insides here of what the constants inside the big O notation is. So it's really off, you know, okay. So what is another representation of the graph? So let's duplicate this page, okay? And let's take another representation of this graph that is not an adjacency list, okay? And a different representation is an adjacency matrix, okay? An adjacency matrix looks like this, okay? So I have a matrix, and the matrix has A, B, C. No, I made it too small. Let's get rid of this and do it again. Someplace where I have more room. Okay, let's do it over here. A, B, C, D, and E. A, B, C, D, E, okay. And A, B, C, D, and E. Okay? So wherever there's an edge between something and another thing, okay, in the matrix, so between A and B, there's an edge. Between A and C, there isn't an edge. Between A and D, there's an edge. Between A and E, there isn't. Okay? So let's keep going with this. Between B and A, there's an edge. Okay? Between B and D, there's an edge. Right? Between D and A, between C and D, there's an edge. Right? C and D, there's an edge. Between C and E, there's an edge. Right? I put a 1 there. Between D and A, there's an edge. Between D and B, there's an edge. Between D and C, there's an edge. And between D and E, there's an edge. And between E and C, there's an edge. And between E and D, there's an edge also. So this is the adjacency matrix here. The implication is that all the entries here that don't have anything are 0 in this matrix. Okay? Okay, so this is an adjacency matrix. Okay? This is an adjacency matrix. This is another representation of graphs. Okay? If the graph gets very big, if like you're thinking of the graph of all the street grid of New York City, the graph is really huge, right? There's going to be a problem with this representation because you have thousands and thousands of vertices, but each vertex is connected to maybe 2 or 3 other vertices only, right? When you look at the grid over here that we just drew, all of these vertices in here, okay, how many vertices do I have? All of these vertices. I have 4 per line, and I have 5 lines. So I have 20 vertices, right? I have 20 vertices, and each vertex looks like it's connected to 2, 3, or 4 other vertices at most, right? Each vertex, like S, is connected to 2 vertices. This one over here, we're going to call it A, is connected to 3 other vertices. It's connected to this one, B, C, and D, right? And then A, it's also connected to D, E over here. So A is connected to 4 vertices. D is only connected to 3. D is connected to S, A, and F. Okay, so if I have a grid that is humongous, thousands of vertices, and each vertex may be connected to 1, 2, 3, or 4 other vertices, okay? An adjacency matrix like this becomes, first of all, very large, and it has a lot of zeros in it. So an edge A, which could have like a vertex A, the row over here for A would go on for thousands of entries, and most of them will be 0. So an adjacency matrix is kind of like wasteful in space, in storage space, because you're putting a lot of zeros in here in order to make it indicate what the graph is. Now, there are ways, there are algorithms which is probably some of the stuff that you would do in graph algorithms, where you would take a large matrix like this, and then they're called sparse matrices, I believe is the right terminology for them, because they have a lot of zeros in them, but they have very few numbers other than zero. So sparse matrices can be compressed, and there are algorithms for working with sparse matrices, but we're not going to discuss that. Okay, so one of the major disadvantages of the adjacency matrix is that it can be very sparse. Okay, here I have 5 by 5, 20 entries in this matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 of them are zero out of 20. Out of 25, sorry. Out of 25, 5 by 5, 25. So out of 25 entries, 13 of them are zero. That's a more than half. And this is a reasonably small graph. So lots of zeros is the main takeaway here for adjacency matrix. Okay. Any questions about this so far? So the most interesting thing about graphs is our ability to travel through the graph. Like we're gonna emulate like a GPS kind of thing. Most of our interest in graphs is if I have a graph like this, we'll draw this new graph, A, and then B, and then D, and E, and F, and C. And then the edges that connect them are A to B, A to D, okay, so these are the edges that connect this graph, okay? And I want to traverse, when we talk about walking through a graph, okay? In other words, starting at a particular vertex, let's say we're going to start at vertex A. I want to find out what the distance is from vertex A to all the other vertices in the graph. Okay, how far is A from D? How far is A from B? How far is A from E, F, and C? Okay, I want to know how far it is to get to all of these vertices from A. Okay, so in order to do that, I'm going to do something called a breadth first search. Okay, now what is a breadth first search? Well, the way it works is the following. Okay, so let's take a look. So the distance from A to itself is 0, right? The distance from A to B is 1, right? There's only one edge that connects A to B. So therefore, I'm at A, I go through one edge. Now I'm at B, it cost me 1 to get there. From A to D, it's also 1, right? To get from A to E, right? E is at a distance of 2 from A. In order for me to get to E, I got to go A to B and B to E. That's 2 steps to get to E, okay? And to get from B to E, okay, is a step of 1. Getting from B to F is also 2, right? Correct? Because going from A to B is 1, B to F is also another 1, so the distance to F is 2. But if I take this other path, the distance from A to F is 3. But really, F is only 2 steps away. I could take a longer path if I wanted to, but it is shorter for me to go about it in this way. All right, so that's what I'm trying to figure out here is the distances. And then the distance from F to C is really also is now 1. So it's whatever the distance was to get to F plus 1 in order to get to C. Okay, so the purpose of breadth first search is for me to start at a particular vertex with a count of 0 and then number all the vertices in my graph to know how far they are from where I'm coming from. Okay, so what is the algorithm for doing that? Okay, so let's write down the algorithm in order to do this, and then we'll walk through the algorithm together. Okay, so we're going to talk about breadth first search. BF. Well, let's write it out first.
Professor.
And that's known as BFS. Okay. So, any questions so far about the breadth first and what I just drew here with before we get to the algorithm itself?
I have a question.
Yes, Eric. Go
Uh,
ahead.
quick question. So this is more efficient than stack because I think this is also like the problem with the airplanes, or it's different.
Say that again. Like, oh, like the example that we did in class with the stack.
Yeah. So this is more efficient than that.
Yeah.
Oh, okay.
And some of these algorithms that we use will use a stack also. Okay. But the stack problem was more of a, okay, how can we use a stack to calculate whether there is a path from point A to point B? Okay. But these algorithms are more optimized for finding such a path. And we're going to visit, but we're going to do breadth first search. We're going to do depth first search. And then we're going to do a shortest path algorithm, which is called Dijkstra's algorithm, which is quite an amazing discovery. So yeah, so that's a good point. That this is very similar to the stuff that we did with when we did the airplane example and showing using how do we use a stack to do this. That's a good point. Okay, we can go back and revisit that if you'd like after we have visited some of these algorithms. Okay, have seen these algorithms. We can go back and revisit that exact same example. It kind of looks like this over here. But let's continue. So what is a breadth first search? So to do a breadth first search, I'm always going to start at a place which is the vertex that I'm starting from. Okay, I'm always going to start from this vertex that I'm starting from. Okay, and what I'm going to need in order to do this, I'm going to need two things. Okay, I am going to need two different things. I'm going to need a queue. So let's get the queue over here. Sorry, we'll use a different color for the queue. So I'm going to need a queue. That's a queue. Okay. And I'm going to need also a list or a set or a list. So this is where you're going to start seeing in graph algorithm us using other data structures in order to accomplish the traversal and the things that we want to do with this with these graphs that we are working with. Okay, so what does the breadth first search algorithm look like? Well, it looks like this. It says NQ, the start vertex. Okay, and add the start vertex to list. Okay, so if I'm starting with A, then I'm going to put A in the queue, and I'm going to add A to the list also. Okay, add it to the discovered list. Okay, discovered set. That's called the discovered list. Okay, we're going to call this discovered list. Discovered list. Okay, and then I'm going to do the following thing in here. I'm going to say while wrong color. While Q not empty do the following. Okay. I am going to go to the Q, DQ, start, DQ current vertex, curve, the current vertex from Q. Okay, so in other words, for us, what does that really look like? Well, my current vertex right now is going to be A, and I'm going to remove it from here, from the queue, because I DQ'd it. It was the first thing in the queue, I took it out. It's my current vertex. Okay, visit the current vertex. Okay, by visit the current vertex, number it. Okay, so we're going to start with num equals 0. Okay, so visit the vertex, meaning assign it the current number. Okay, so this becomes 0 now. Okay, so visit curve, assign it the number, assign it num plus plus. Okay, so it gets 0 and now num becomes 1. Okay, so let's keep track of num over here. It was 0, now it's 1. Okay, we're good so far? Okay, for each vertex, okay, adjacent to the current vertex, okay, and now I'm going to say for each vertex, for each V adjacent to curve, do the following. Okay, do the following. For each vertex adjacent to the current vertex, do the following. If the adjacent vertex is not in discovered list, okay, if it is not in the, so what are the adjacent vertices to A? They are B and D, right? They are the two vertices that are adjacent to A. Neither of them is in the discovered list, okay? If it is not in the discovered list, NQ, adjacent vertex, and add adjacent V to discovered lists. Okay, so the two vertices that are adjacent to A are B and D. So I'm going to put them in here, B and D, and I'm going to also put B and D in the discovered list. Okay, so we're good so far? Now let's see what happens for the rest of the stuff in here. Okay, we have added B and D to the list. So now we'll go back up to the top, to the while loop, right? We're back here at the while loop, and we got to DQ the current vertex from the queue. Well, this thing's B was the first number that went, the first one in here. So B is my current vertex. Okay. And while the current vertex, so DQ, visit the current vertex. So B gets the number 1, right? Gets the number 1. Okay, I'm not going to do it this way because this is wrong. Okay, so I'm going to just say visit the current vertex, which means give it the distance that it needs to get, and the distance that it needs to get is 1. Okay, that's the current number. Okay, and so B gets a distance of 1, and then for each vertex adjacent to the current vertex, okay, so what are the vertices adjacent to B? The vertices adjacent to B are A and E, right? These are the two vertices that are adjacent to B. B says, if A is not in the discovered set, okay, so it looks at A first. It says, oh, A is in the discovered set, so I don't need to worry about it. I've already discovered that vertex, okay? E, is that in the current vertex? Is that in the current discovered list? No, it's not. So I enqueue E. I enqueue E over here, and I add E to the discovered list. Okay? And now I'm done with B. I go back to the top of the while loop. I dequeue D. So D is my current vertex. And it says, okay, visit current vertex. Well, give it a distance of 1, right? And then keep going. For each vertex adjacent to V, to the current vertex. So what are the vertices adjacent to D? Well, it's A. Okay. For each vertex adjacent to V, okay, if the adjacent vertex is not in the discovered list, okay, well, there is no vertex here that is adjacent to D that is not in the discovered list. So I'm done with D. Okay, there's no more to do over here. So now go back up to the top of the while loop and pick up the next current vertex. Well, I'm going to dequeue E in this case. Okay, E is my current vertex. And what can you reach from E? Well, from E, it looks like, oh no, there was, when we were at B, we were supposed to put F in there too. Okay, so F is still in, well, let's backtrack a little bit. Okay. So here we are. B and D were in the list. Sorry, I'm backtracking a little bit. Okay. B and D were in the list because you could get them from A. Current vertex now is B. Okay, which means the current vertex is B, which means who can be reached from B? Well, A, E, and F. So I'm going to add A. Not going to add A because, okay, so I'm going to look at A. Is A in the discovered list? Yes, it is. Okay, don't touch it. Okay. B, B is in here, okay, because it's discovered, and D is discovered also. They were both put there, okay, when they were put into the list, B and D. Okay, so I'm going to look at A. A is in the discovered list. No worry about it. E, it's not in the discovered list, so I'm going to enqueue E and put E in the discovered list, and I'm going to enqueue F and put F in the discovered list. Okay, so I'm done with B. I've given it the number 1, right? And now I go back and dequeue the next element. The next element is D. Okay, the next vertex is D. Okay, the vertices that can be reached from D are A. That's the only one that can be reached. Is it in the discovered set? Yes, it is. There's not number D as 1, and keep going. Okay. So now I go to E. I dequeue E. So my current vertex is E. And the vertices that I can reach from E are B and F, right? So is B in the discovered set? Yes, it is. Is F in the discovered set? Yes, it is. So I don't need to do anything over here. I just need to number E as 2. And I need to continue. DQF. He's my current vertex now. Okay? F is the current vertex now. So what are the set of vertices that I can reach from F? Well, there's C and B, right? Well, B is in the discovered set, so I don't need to do anything with it, but C is not, so I'm going to add C here and C there. Okay? And now I'm done with that. I go up and I DQ, I visit F, meaning I give F a 2 also, because it is a distance of 1 from B. And then I DQ C, becoming my current vertex now. C is my current vertex. What are the vertices that I can reach from here are F, okay? Well, F is in the discovered set, so I don't need to do anything with it. So I'm done with C. I give it that number 3, okay? But then I go back to the top of the while loop and it says the queue is empty now, so I'm done. So I have numbered all my vertices the right number, okay? They are all a distance away of breadth, of width, you know, going from where I am. It's going to take me 3 steps to get to C. That's what I know from looking at this graph. It's going to take me 2 steps to get to E and F, and it takes me 1 step to get to D and B. So this is actually very helpful to see if there is a path to get, because at the end of the algorithm, if there was a vertex over here, G, if there was a vertex G over here, okay, this is a valid graph too. G is unreachable, right? At the end, when I'm done, I'll find out, oh, I can't reach G because G never got a number. He was never visited, okay? Or I could have a disconnected graph where there's G, which is connected to H and connected to I. But this graph of GHI is a separate graph. It's a part of my graph, but it's disconnected from my current graph. From A, B, C, D, E, and F, G, H, and I are a separate graph. They're disconnected. So when I do the breadth first search, I'll discover that G, H, and I are unreachable from me, from A. And they'll also be unreachable from B, C, D, E, and F. But when I get to doing vertex I, G, H, and I will find out from those cannot reach the other graphs, the other vertices. So this is how you do breadth first search. And the benefit of breadth first search is it tells you the connectivity. Who is connected, who is not connected, who you can reach and who you cannot reach, and how many steps it takes you to reach them. Okay, good. Any questions? Questions? All right, let's continue. So breadth first search is an algorithm that is very important in graphs. The other algorithm that is actually important in graphs is the depth first search. Okay, now how does depth first search work? Well, let's take a look. Okay, so we're going to take another graph or the same graph. We'll take the same graph. Okay, and the same graph is essentially A, B, C, D, E, and F, and it's connected like that. Okay, this is the same graph that we had. And now we want to traverse this, okay, in depth first search. Okay, so I'm going to start at A. Okay, where am I going to go from A? I can go to B. I can go to F. Okay, I can start at A. I can go to B. I can go to E, and I can go to F. And from F, I can get to C. Okay. That's how you do depth first search. And then you go back and you say, well, I can also go to D and I can also go to F from this way. And now I've finished traversing my graph in depth first manner. Okay, so how do we do that? What's the algorithm for depth first search? That clearly is going to give us a different notion of this graph than we had with the breadth first search. So now we're going to do depth first search. Depth first search. DFS. Okay. We always got to start with a starting vertex. Okay. So DFS of start vertex. Okay. And we're going to start with A. A is going to be our start vertex. Okay. And here we're going to need two data structures. Okay. We're going to need two data structures again, except that now instead of a queue, we're going to use a stack. Okay. We're going to use a stack. And then we're going to use the same thing that we used earlier, which is our list. Okay. List of visited vertexes. Okay. So I have a stack and a list of vertices. Okay. And the first thing that we do in our algorithm here is push start V on stack. So A goes on the stack. Okay. And now I'm going to ask the question while stack not empty, do the following. Okay. Current cur V, the current V is equal pop stack. Okay, so that's the current V. In this case, becomes A because I just popped it off the stack. Okay. If the current V, if current V not in visited list, notice that this can be a list or it can be this other data structure called a set. You guys familiar with sets? We haven't discussed the data structure called sets, but you're familiar with the concept of a set, right? If you're not familiar with the concept of a set, so if I have the following numbers and I want to put them into a set, if I have the following letters and I want to put them into a set, A, B, D, E, G, C, B, A, F. Okay, I want to put them into a set. What does the set contain at the very end? Okay, a set at the very end, if I put all of those vertices in it, it has A, B, okay, D, E, G, C. Now, when I go to add B again, B will not get added again because B is already part of the set. When I go to add A again, it says I can't add it again because A is, well, it doesn't say no, I can't. It just says, all right, okay, fine. A is already in the set. There's no need to add it. And then F, okay? So the set is basically unique. Every element shows exactly once. Even if the element occurred multiple times when I went to put it into the set, it only shows up in the set once. So I could use, instead of a list, I could use a set, but we're not going to worry about that right now. Okay. If the current vertex is not in the visited list, okay, so visit the current vertex. Visit current vertex. Okay. So what does that look like? All right. What does it mean to visit the vertex? It means that I give that vertex a number, right? So I start with 0. Okay. A is going to be marked with the number 0. Okay. And visit the current vertex. So I am going to also build up a list over here, which is the order in which I'm looking at these vertices. Okay, order. The first one I visited is A. Okay, so A has been visited. Okay, because it's in the order list here. Okay, and now, but after I visit the current B, for all the adjacent, for adjacent V to cur V, anything to adjacent to current vertex, okay, push adjacent vertex on stack. So what are the adjacent vertices over here? Well, they're D and B, right? And A has been visited, so we mark it as visited, okay? And we put it into the traversal ordering. A is the first one that we have traversed, okay? So, okay, so let's go back. So we have pushed the B and D onto the stack, okay? And now I go back up to the top of the while loop, pop the stack. What's at the top of the stack? It's B, right? Remember, a stack is not like a queue. So I'm going to take B out, okay? If the current vertex is not visited, okay, visit the current vertex. Well, B is going to go in here, and B is going to go into the list of the vertices that we have visited, okay? So B has been visited, which means I put it into the visited queue, okay? And I put it into the visited list and into the order of the vertices over here. And then I go and find out all the vertices that I can reach from B. And what are the vertices that I can reach from B? Well, there's A, right? There's E, and then there's F, right? I pushed A, I pushed E, and I pushed F onto the stack, okay? And I go back up to the top, get the next vertex. Well, the next vertex in the stack is the one at the top of the stack, so it's F, okay? And now I'm gonna, so my current vertex is F, okay? If it's not in the visited list, then add it to the visited list, F and F. Okay, they're both, it's in the order of visiting the vertices, A, B, F, okay? And then from F, what are the vertices that we can reach from F? Okay, well, F can reach, F has been visited, okay? So what are the vertices that we can reach from F? Well, we can reach B, E, and C, right? B, E, and C, correct? From F, we can reach B, sorry, C, B, yeah, from F, you can reach C, B, and E, right? C, B, and E. So I go back up to the top. I DQ the next, the vertex from here. Okay, I push them into this order. The next vertex is going to be E, right? Because that's C, sorry, is going to be the next vertex. That's the one I removed from the top there. C is my current vertex. So visit C, right? And then every vertex that's reachable from C. So I put F in here again, right? Because that's the only one that I can reach from F, from C. Okay, and I'm done with that. I go back up to the top. And now I pop the search thing again. F is my current vertex, but F is in the visited list, so I don't need to do anything with it. I keep going. I pop E. E is my current vertex. Is E visited? No, it's not. So let's visit E. So we're going to add E to the list and add E over here also. Okay. And now, what are the things that I can reach from E? Well, I can reach B and F. Okay. Now go back up to the top, pop the next vertex, F. Is my current vertex is F. Has F been visited? Yes, it has. So F has been visited, so there's nothing to do in here. Pop the next vertex from here. B. Has B been visited? Yep, B has been visited. There's nothing to do over here. Pop the next one. It's B again. It's been visited. Nothing to do over here. Pop the next one. E. E has been visited. Right? Nothing to do in here. Pop the next one. It's A. A has been visited. There's nothing to do here. Pop D. D has not been visited. So D gets added to the list, and D gets added to the list over here. And now when I go back, and it's anybody that can access from D is A. I push A. I come back to the top. I DQ. I pop A. A has been visited. There's nothing to do here. The stack is empty. I have visited all of my vertices in depth first manner. Okay. This is what depth first search will do. It'll give you the order in which you can access these vertices, but by going as deep as you can first, and then coming back to the ones that are reachable in closer distances. Okay, so depth first search algorithm is right here. Any questions on that?
I have a question. I'm not really sure if it makes sense, but which one would be more convenient, like breadth first search or depth first search, like between the two?
It depending what you're trying to do,
Oh,
right?
okay.
It really depending on what you're trying to do. Breadth first search basically is a way of going about numbering the vertices in order away from the start vertex. Here, we're looking at, how to get to all of the vertices, but by going as far as I can first, and then coming back and looking at the ones that are closer to me. Okay, I'm going to try to go as deep into the graph as I can. I'm going to visit my neighbor, and then I'm going to visit their neighbor, and I'm going to visit their neighbor, and I'm going to visit their neighbor before coming back and visiting the other ones that are closer to me. Okay, I'm trying to go as far as I can first, as opposed to visit everybody next to me and then visit everybody next to them and then spread out that way in the graph. It's just a different way of walking through the graph. Okay.
Oh, okay. Thank you.
Sure. Anybody else? Okay, let's continue. Okay. The next thing I want to talk about is, so far the graphs that we have been drawing have been edges that have no direction. There's no direction to the edge. In other words, if I look at these edges in here, I can go from D to E, or I can go from E to D. I can go from D to C, or I can go from C to D. Sometimes we're interested to show that there is direction to the graph. Okay, there are directions. So I can have this graph. Okay, I can have A, B, C, D, E, and F. A, B, C, D, E, and F. And I can go from A to B, B to C, C to E, E to F, right? I can go to A to D, and D to B, and B to E. Okay, so this is a directed graph. Okay, if I am at F, I can't get to A. Okay, If I'm at F, I can't get to A. If I'm at E, okay, I can get to F, but I can't go anywhere else. If I'm at A, I can go to B, D, okay? If I'm at B, I can go to, if I'm at D, I can go to B. If I'm at B, I can go to C and E, so on and so forth. So edges now have directions. If you can get between two nodes in either direction, then the graph will have two edges. So I can go from A to B, or I can go from B to A. Okay, so this graph here has two edges between A and B. It's a directed graph. Okay, the edges have direction. You could imagine that for your GPS program, one-way streets will be one edge. Two-way streets will be two edges, right? So if a street is going one way from A to B, from this intersection to that intersection, that's a one-way street. This is a two-way street. Okay? So GPS definitely uses directed graphs. Okay? So directed graphs are, you're interested in directed graphs, you want to know if there are cycles. Okay? Cycles this particular graph doesn't have any cycles. Well, it does have a cycle in it, right? I can go from A, in this case, I can go from A to D, D to B, and B to A. That is a cycle. Okay? So a cycle is a path that starts and ends at the same vertex. A directed graph is cyclic if the graph contains a cycle, and acyclic if the graph doesn't contain any cycles at all. Okay, so this graph that we have over here is cyclic because it does have a cycle in it. Okay, cycles are interesting because they could be a problem when it comes to us finding the shortest distance. Okay, so if I want to go from A to F, will my algorithm get stuck going from A to D to B to A to B to D from D, A, D, B, A, D, B, A, D, B? That I'm stuck in the cycle. Okay, I don't want to get stuck in a cycle when I'm moving around in a graph. Okay, so understanding cycles is very important to understanding how to find paths to get from one point to another point. Okay, so directed graphs are a form of graph that we are going to work with. Okay, that they are very much at the heart of what we do in graphs. Okay, the other thing is that the edges themselves have weights. Okay, so the edges could have weights. So here's a directed graph, and the directed graph has no weights in this case, but I can assign weights: 3, 2, 1, 4, 5, 2, 6, and 4. Okay, so now what is the cost of the path? Okay, the shortest path that takes me from A all the way to F. Okay, what is the cost of the shortest graph that takes me from A all the way to F? Let me just redo this for a second. Okay, I'm going to assign that edge a weight of 6. Okay, so what is the shortest distance from A to F? Okay, if I go to A to B, that's 6, right? Plus 5. From B to C, from B to E, plus 4. That comes out to 15. Correct? That's A, B, E, F. Right? This is the path from A, B, E, F. Is there a shorter path? Well, what if I go to A, to D, to B, to E, to F? It's more vertices, but is it a shorter path? Well, let's see. A to B, D is 3. plus 2 plus 5 plus 4. Altogether added up, it comes out to 14. So really this is a shorter path, right? To get from A to F. I have another path that goes from A to F. I can go A, D, B, C, E, F. That's another path, right? So how much is that? A to D is 3 plus 2 plus 2 plus 6 plus 4. So 10, 14, 17. So clearly the shorter path is this one, okay? To take me from A to F. So now these weights are actually interesting, okay? Because like the distance between A and B in one direction is 6, but in the other direction it's 4, okay? Does it mean that A is a distance of 4 or 6 away from B? It depends on which direction you're going. If you think of it in terms of GPS, okay, two-way street, there's traffic in one way going from A to B. There's a little bit more traffic than there is. So it's going to take me 6 minutes to get from A to B going that direction. But there's less traffic going the other way. So it's going to only take me 4 minutes. Okay. So weights can be the amount of time it takes to get from one point to another. Okay. How does GPS calculate these numbers? Well, GPS basically aggregates all of the GPS information that's coming from all of the cars that are in the area in which you're in, or have just recently been in the area in which you're in. Because if the cars around you are all beaming up to GPS, you guys know how GPS works, right? GPS works by location. Okay, global positioning system. There are 3 satellites up in space, and they are in geocentric orbits. In other words, they stay where they are relative to Earth. And what you do is your device sends a signal up into space, and it goes to all 3 satellites. Each satellite measures how long it takes for that signal between you and that satellite, okay? So I have 3 distances from where I am the point. I go to one satellite, another satellite, and another satellite, and they're all different distances. So between the figuring out how long it took for the signal to each one of them, the satellites can position you on Earth exactly where you're supposed to be, or exactly where you are. This was developed for military purposes. And initially, when it was developed for military purposes, any military user of GPS would get accurate information as to the location. But civilians who were using GPS early on, they would introduce a fudge factor in it. So it would give you your position to within so many feet of where you are. Not exactly where you are, but so many feet of where you are. Okay, so that way it was reserved for just military purposes as far as accuracy. But now that we have GPS where everybody needs to know exactly where they are, that's been opened up. So now everybody gets accurate positioning. So GPS works that way. All of these devices are constantly beaming information up to the satellites and constantly getting readings back. Reading back, reading back, reading. Okay, here I am, I'm in this location. And then later on, it took you a minute to move 100 feet, okay? And everybody else around you who is moving in that same direction, it took them a minute to go 100 feet. So it says, this is slow going in this direction. And it's going to take so many minutes to get between A and B. It's going to take 6 minutes to get between A and B going in this direction, because everybody around you is reporting that it's taking them that much time. And traffic going in the other direction is encountering less. So it aggregates all of the information, and Google and all of the other providers basically aggregate this information and then give you an estimate as how long it takes to get from one point to another. Okay, there are algorithms that we're going to look at that will actually tell us how does the GPS find the path for you to go from point A to point F, because it clearly has to visit all of these three paths in order to find out which one is the shortest one to recommend to you. And GPS is doing it based on how much time it's going to take you, because clearly the distance between A and F is constant. If it gives you just the shortest route as far as distance, okay, maybe there's traffic along that route and it'll take you longer to get there than it would be to take a slightly longer route. And I'm personally one of those people, if there is traffic, I would much rather drive a longer distance and get there first rather than be stuck on the short distance and be stuck in this traffic. Okay? So weighted graphs are very important in GPS usage and in graph algorithms in general. So that is weighted graphs. Any questions on weighted graphs or anything that we have talked about as far as graphs are concerned? Okay. There's an algorithm that I want to talk about, and it's called Dijkstra's algorithm, but I'd rather save that until Monday to talk about it. Okay? It's going to take us a while to walk through this algorithm and understand it really well. So I'd rather for us to wait for Monday. Any questions? I'm going to stop sharing the screen.